And by the way, I would like to comment because when I was a student, we always know that students are always a better problem solver than the instructor. You know, because they are doing all this homework. I'm not doing homework at all, right? So you should be better than me. We should think about, okay, if you cannot do it quickly, I cannot do it. Well, I learned these things many years ago, right? So you are currently learning. Because I guess this is a wrong. I don't like this idea that you think that professor, you shouldn't be better than professor. Okay. In fact, you're learning things. Okay, are expecting that after you're learning these things, you should be better than professor. Okay. Otherwise, civilization, the human being cannot be better and better, right? Now, after we learn many things, we even can say we know physics better than Newton, right? Of course, we're not smarter than Newton, but we know many things more than Newton knows. Because, okay, he's home, right? So, we should have this kind of orientation. You need to do a better job than me, okay, for at least these kind of stuff. I hope you have this kind of ambition. Okay, now, let's look at
on the slide on Blackboard.
yes, it's already on Blackboard now. So we are going to start with energy and the momentum. So before that, we have talked more about the vectors. So we already talked about how to add vectors together, okay, by components. Now we're talking about how to multiply vectors together. There are several different kinds of multiplication products formed by the vectors, okay. The first one, the most simple one, is if you try to multiply a vector by a scalar, okay, the result is still a vector. And if you try to multiply a vector by another vector, you have two kinds of operation. One is called scalar product, or dot product, or inner product. So after this operation, if you put two vectors together with this kind of operation, you will get a scalar. And another kind of product is called the vector product, or cross product, or outer product. Okay, after this kind of operation, you are going to have a new vector. Okay, so we have three kinds of product. So here, I would like to note that I prefer these names term instead of the scalar product and vector product, because sometimes we may confuse this with this one. Okay. So dot product or inner product is one kind of operation. Cross product and out product is another kind of operation we need to talk about. Okay, first of course, let's look at the most simple one. If you you multiply a vector by a scalar, it's very easy to understand in the component form. Okay, so if you have a component, a vector A, and a scalar S, it will be some number. Okay, 2, 5, 10, whatever number you may have it. You can see with the simple or straightforward algebraic manipulation, if you write the vector in the standard form and you put the number here and then you just multiply out, so you get SAX I cap, SAY j cap, SAX k cap. So you can see that you just change each component with the same multiple, right? Okay. So if it's 2, so it double every component. And as a result, you can see it will change the magnitude of the vector. In fact, okay, if it's 2, it doubles magnitude. And one thing, please note that this S can be a positive number or negative number. If it's a positive number, the new vector still be in the same direction. If it's a negative number, the new vector will be in the opposite direction because it will introduce a negative sign in front of the vector. Okay. Another note is that even the component in form itself can be regarded as a vector multiplied by a scalar. Okay. So you can think about I cap multiplied by some scalar, j cap multiplied by a scalar, k cap multiplied by some scalar, and put them together and add them together. Okay. So that's a component form. So in another words, we can think about any vector can be regarded as 3 vectors added together. A vector along x direction, a vector along y direction, a vector along z direction. And each of the vector can be regarded as a unit vector multiplied by the component. Okay, ax, ay, az. So this is a vector multiplied by a scalar. Now let's look at the inner product or dot product. Why it's called the dot product? Because we know we use a dot to denote this kind of operation. And another one is called cross product. So it denotes another kind of operation. So for vector, these things are not the same. Okay. For numbers, we all denote them they are the same thing, multiplication, right? But for the vector, we have different kind of product. So this is the inner product. This is the outer product. With a star, or if you just put them together without any sign, that means scalar multiplied by a vector. Okay, so please note that we have different multiplications. Any question here? So how can we calculate the inner product or dot product? So if you have A dot by B, it will give you a number, a scalar, which is A multiplied by B multiplied by cosine theta. Theta is the angle between A and B. Okay? And the geometrical meaning of the dot product is that, okay, now you try to multiply by the vector A and B together, but they are not in the same direction. So only part of the, say this is B, only part of A is along the same, which has the same direction with B. So when we try to form the inner product or the dot product, we use only that part of vector A. So it's a projection of A along the B direction. So it's A multiplied by cosine theta. Okay, so that's why you get A multiplied by B multiplied by cosine theta. So you can think about the projection of A multiplied by B. This is inner product. So it considers the contribution when the two vectors have the same direction. Okay. And so you can see because the inner product is given by A multiplied by B multiplied by cosine theta. Here A and B, they are magnitudes. So both of them are positive number. But cosine theta itself can be positive and negative. So the inner product A dot B can have some sign, positive, negative, depends on the angle or depends on the direction of both vectors. Okay? So you can see, of course, if in some special case, if A is parallel with B, Then A dot B is simply you multiply the two numbers. It will give you the maximum value of inner product. If A is anti-parallel with B, then you get negative AB for the inner product. It's a minimum number for the inner product. If A perpendicular to B, then the angle theta is 90 degrees. Cosine 90 is 0. So regardless of the value of A and B, it's always 0. Okay. In fact, later when you start with analytical geometry, if you want to see if two straight lines are perpendicular to each other, usually the way is to calculate the dot product of the two lines to see if they are 0. If it's a 0, dot product 0 is perpendicular. Okay. And another thing, scalar product is commutative because it's A multiplied by B cosine theta. If you switch it, B multiplied by A multiplied by cosine theta, same thing. So it's commutative. But cross product is not commutative. Okay? So this is the part that we'll stop here.